Hi everyone, welcome back to Math 261. This is Scott. Let's get started. What we're going to look at in this section, which is 1.6, is some applications of linear systems. So these are just a couple little applications. The biggest, most important applications of linear algebra are going to be happening a little bit later in the course as we develop more tools. But here, just with what we've got already in this first little week and change of class, will enable us to answer some interesting questions from the worlds of, first off, economics, second off, chemistry, and then thirdly, what's called network flows. So applications of linear systems. And before we do any of this, we're going to take a nice little opportunity now to see finally how to get technology to ease some of the burden of drudgery from us. So what we're going to look at now is row reduction, via TI-89 style calculator. So TI-89 is kind of the official calculator of this class, and in particular, most importantly for making this video, it's the kind of calculator I happen to have handy so I can show it to you. Now, if you have a TI-83 or 84 style calculator, then here's my advice for what you can do to find a good little description of how to do the row reduction process in that. So for TI-83 or 84, what I would recommend is there's a little web page under Math Boot Camps that gives a very good step-by-step explanation of how to do this for a TI-83 or 84 style calculator. It's the same in both. So Google row actually I should say Math Boot Camps. Row reduction TI 83 or TI 84. So probably you don't need to put in all of that, but that should be more than enough to get you to the page. That's a Math Bootcamp's site that will they'll give you a step-by-step primer on how to accomplish this on a TI-83 style or TI-84 style calculator. For us though, what we're going to look at is a TI-89 style calculator. So first off, let me give you some little tips on how to enter matrices. So there are different ways of doing this, and if you look online, you'll probably get all sorts of different approaches. But here's what I think is the easiest way to enter a matrix on a TI-89 style calculator. So first off, entering a matrix. So the format, so again, we're talking about a TI-89 style here. So entering a matrix. So the easiest way to do this is to use square brackets and then 1, 2, let's say 3, and then if you use a semicolon, then what that does is that ends the row. Let's say 4, 5, 6. Another semicolon will end that row. And then let's say we have 7, 8, 9. And then you end the square bracket. What that would produce, so this would produce then the matrix that looks like this. 1, 2, 3 as its first row, 4, 5, 6 as its second row, 7, 8, and 9 as its third row. So you use you use commas to separate entries, and then semicolons. These end the row. So this is the easiest way to do it. And so, for example, if you have a calculator such as this, clear away all the riffraff that might currently be on it, and let me just quit. And if you are just here, you just go first to home, and you can just hit enter while home is selected, or let me see if I can reduce that glare a little bit. And close enough. So you can either hit enter while home is selected, or if you just press the home button, then no matter what screen you're on to start with, that will take you to here. And then the square brackets are right above the comma here, and you'll notice they are the color of the second button. So on my calculator it's blue. Your mileage may vary on that, but for the square bracket you just do second and then the comma button. And if you do 1, 2, 3, then I want to do the semicolon. You'll notice that is right below on the 9, and it's the color of the second button, so you do that. And then I do 4, 5, 6, and then let's say I want a break on the row, so then that looks like that. And I want 7, 8, 9. And then I press, and I do that. So then that, you'll notice, has entered into the calculator the matrix. However, it has not actually done anything to the matrix. If you want to actually do things to the matrix, then you'll have to actually find the place where you can do math on these matrices. So here's how to do that. So if you want to actually do math on the matrices, you may or may not find it convenient to actually name the matrix. So if you want to store the matrix to a variable name, or to just a name, then here's how you can do that. So storing a matrix to a name, what you can just do is you have your matrix, and it says whatever it says, da 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 da, maybe with semicolons in between. There are other ways of doing this, by the way, so if you already have a way that works for you, no big deal. And then you use the little arrow here, which you get by doing the store button. So that means store it as a variable. So that's the STO for store, and then a little triangle. So that means store it as, and then you can here pick the name. So here you can make any old name you want, and you use alpha in order to access the alphabetic buttons. So you could just call this like A, for example. So the way you do this is you'd hit the alpha button, and then you would find the one that has the name you want. So here, for example, if I wanted to store this as A, I would press the store button. Zoom in a little bit. I'd press the store button, and then I would give it the name that I wanted. So alpha A. And then I press enter. And so now that is what, so if I clear this, then I do alpha A. So that is now what is stored under alpha A. So the A refers to this. Now, so this is just an example of a name that you could choose. You could, it can be more than one letter long, you can be any letter, and as long as you keep on typing without any symbol in between, it will be fine. It can be multiple letters long. So you can store a matrix to a name such as A, and then doing math with a matrix. Here, what you want to do is you want to hit the math button, so second plus the button that has the math on it. So that's the 5 button. So second and 5, you'll notice it says math. And so if we do that, let's see where that takes us. So just clear that, not that it needs to be done, but the second and then 5 is math, and you look over the list of options here, and you'll notice matrix at number 4. And at that, there will be a bunch of options here, only only 2 of which currently make a lot of sense to you, although by the end of the term we'll understand a lot more. So there is the T, which is transpose. That's where we'll discuss that later. So then there's also the determinant, which we'll also discuss later. This puts it into an echelon form, but not reduced, just row echelon form. This one puts it into reduced row echelon form. And then there's some more stuff. This one, and then here, this one gives you the option of augmenting a matrix by something else, which is interesting. And then these are eigenvalues, eigenvectors, and other stuff that we'll learn the use of as the course progresses. But the important thing for us right now is reduced row echelon form, for example, or possibly augmenting. But then we have, these are various operations. That we can do. So for example, let's say I wanted to row reduce something, and it was a little bit less friendly than some of the things we wanted to do before. So let's say find the reduced row echelon form for, and let's say the matrix A looked like, let's say we had 4, 1, 7, 3, 2, 6, 6, 1, 1, 5, 0, 2, 2, 3, 8, and let's just say we had something like that. Now this would be a hassle to actually row reduce by hand. Not the worst. I mean, it wouldn't be awful, but you know, who wants to? Like here we have not great options for pivots. We have they're going to have to be fractions involved, and it's just going to be more trouble than we necessarily want to expend on it in most circumstances. And that's of course what the whole point of technology even is. So let's now figure out how to get technology to do our bidding in this. The purpose of technology is to free us up from the drudgery and toil of all of these repetitive tasks. So let's give this a try. So what I can do here is I can just go 4, 1, 7, 3, 2, and then break the row, and then 6, 6, 1, 1, 5, and then break the row, and then 0, 2, 2, 3, 8, and then end the matrix. And it's always a good idea to just type it once and make sure that it comes out the way you want it. There are no typos, you're not missing an entry. A common thing that might happen is if you accidentally miss an entry or you have some kind of typo like this. Let's say we take out that 2. Say we were typing and we've missed that 2 that ended the first row. Then the kind of error that you'd get that would be a signal on that is it would say syntax error, and that's a clue that somehow our matrix doesn't quite make sense to the calculator, and you'll notice that right where it put the cursor to indicate the syntax error was right here, which meant that after it had the first row, it thought that we were talking about a matrix that had 4 columns, and so after it got to the end of the 4th column of the second row, it got confused because another number came, and so it went into a tailspin and it didn't know what was what. So that's the kind of error message you'll get if there was an error in entering your matrix. But here it is. Here it is entered the way I intended. And so now, once I know that that's good, I can just press the right button so that it puts my cursor on the very edge of the line there. And then I can hit the store button, and I can now call it whatever I want. I can call it A if I wish, and that is it doesn't matter if that has already been named or anything like that. It will still overwrite that, and even if it was named, and even if it belongs to a different category, it will overwrite it with now this, and it doesn't care. So then once we have this, then we can clear that. Not that we necessarily need to, but it's always good to have a clean workspace. And then we can scroll down to matrix, scroll down to RREF, and then just put in alpha and A. By the way, you'll know when alpha is indicated because down there you'll see the little letter A to mean that it's the alphabet that is being done. So A, and end the parentheses, press enter, and here what we've got is the reduced or echelon form, and from what the answer is here, we know that the work would have indeed been terrible. There is no good row reduction that you can do. It's going to end you up with denominators like 112ths, 14ths, 56ths, 7ths. It would have been awful. However, we didn't have to do it. We let our little technological assistant take over the boring part of this operation, and then we were able to sit back and enjoy the fruits of its labor. So, just writing down here, so it's in the record. So 100 negative 81 112ths. I'm just writing down what it says in the calculator. 31 14ths. 0 1 0 43 56ths. 27ths. And then 0 0 1 41 56ths. And then 8 sevenths. Now let's look at one application of a way we can make use of the reduced or echelon form of a matrix to match a certain circumstance in the real world. So here's a case from the world of chemistry, and it has to do with balancing chemical equations. So for those of you who have been deep in the weeds of chemistry, you will know that you don't need to use any linear algebra in order to do this. But it is there's a nice linear algebra approach to the subject of balancing chemical equations that you can now make use of whenever you're busy doing chemistry and you just need a quick balancing of an unbalanced chemical equation. So when a chemical reaction happens, frequently it would be written in an unbalanced way, where the proportions of the different molecules are not necessarily given to you. However, if you wanted to actually quantify the reaction, you need to give it in a balanced way, so that you'll be able to put the relative moles of one particular molecule into correspondence with the relative number of moles of the other molecules. So let's just take an example of this, or let's just describe our approach here. The idea is, if we have an unbalanced chemical equation. For example, let's say as an example, we'll just take something like the burning of propane. It doesn't actually matter. It doesn't matter what the for our purposes, it matters obviously in the real world, but for our purpose, it doesn't matter what the actual chemical reactions are that we're talking about here. The math will all work out the same way, but just for the record, here we might be talking about burning propane. So we have an unbalanced chemical reaction, namely we have propane, which is C3H8. And when you burn something, that means combining it with oxygen, so O2. And then as a result, you get the two standard outputs from a combustion reaction. You get CO2 and you get H2O. Now the question is the proportions of each of these molecules that have to go in and which come out. So this would be an example of an unbalanced chemical equation. We do not have the relative weights of each of these given to us here. So it's up to us to find out. So then what we can do is we can assign each molecule a variable, and then what we can do is we can turn each molecule into a vector by using a consistent ordering of the elements. So assign each molecule a variable and write each molecule as a column vector using a consistent ordering of the elements. So going to our example here, it's going to be X1 is going to be the one that's going to go with the propane, let's say. So it's going to be X1 C3H8 plus X2 times O2. So those together are going to make X3 CO2, and then plus X4 H2O. Now the three different elements that are in play here are carbon, hydrogen, and oxygen, and you can put this in any particular order, just stay consistent after that. And let's just say we'll go in the order that they are written here. So let's just say that our vectors are going to look like, sorry, not x's. Let's say our vectors v are going to be, let's say, carbon followed by hydrogen followed by oxygen. And it's good to just write this out somewhere so that you have it nice and clear in what happens next, that this is going to be the layout: carbon, hydrogen, oxygen. So then, we can now turn this chemical equation into a mathematical equation. So x1, carbon, it's going to be 3 of those. So you just read off from the subscripts according to usual chemical notation. This is going to be 3 carbons, 8 hydrogens, no oxygens for the propane, plus x2, 0, 0, 2, equals now. So now we're actually talking about a math equation, not a chemical equation. So x3, and then that's going to be 1, 0, and 2 for the carbon dioxide, plus x4, and now what we have is 0 carbon, 2 hydrogen, and 1 oxygen. But this is not written in the in any of our usual standard forms. So what we can do, is we can move everything to one side to put it into a standard form. So then x1, 3, 8, 0, plus x2, 0, 0, 2, minus x3, 1, 0, 2, minus x4, 0, 2, 1, and that's going to all equal 0, but this is actually still, and this actually now is 0 vector, 0, 0, 0, everything's in balance. So this still actually isn't quite standard form. We want it to be plus, 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 so we can distribute in the negatives, and we'll have x1, 3, 8, 0, plus x2, 0, 0, 2, plus x3, negative 1, 0, 2, and then plus x4. And we're writing this out in a lot more steps than we would in the wild. In the wild, we would basically cut straight to the chase. But here we have, and equals 0, 0, 0. And so then essentially the goal would be to just write it as a matrix: 3, 8, 0, 0, 0, 2, negative 1, 0, 2, 0, negative 2, negative 1, 0, 0, 0. And we can just row reduce this, RREF, to get whatever the answer is going to be. And here, once again, just let the calculator do the talking for us. We don't have to be mathematical heroes here. We don't have to go around row reducing this, which has no great options for pivots that are going to be easily divisible in a non-fraction way. So we can just put it all in here and let the math do itself. So 3, 0, negative 1, 0, 0, semicolon, 8, 0, 0, negative 2, 0, semicolon, 0, 2, 2, negative 1, 0, square bracket. I'm going to store that once again. I'm just going to use A always until I have some reason not to. And I'm going to make sure it came out the way I wanted. And it looks like it did. Oh, wait though, wait. Looking at that, I noticed a typo. It should be negative 2. Probably you were all screaming this at the top of your lungs, pulling your hair out. And that should also be a negative 2. When I distributed the negative, it should have gone to both of those. So I'm glad I did that, because looking at that, It made me realize something that all is not well here. So what was that? That was in the third row. It was the second two. Fix that. It's good. Good life lesson there. Always look at it, make sure, and then so measure twice, cut once on all this, and then once you think you've got it right, then you go to the row reduction, and you can just put in the alpha and A, and here we have 1, 0, 0, negative 1/4, 0, 0, 1, 0, negative 5/4, 0, 0, 0, 1, negative 3/4, 0, and what this means then is that we've got one free variable on the x4, and that means x1 plus negative 1/4 x4 equals 0, which means x1 equals 1/4 x4. Over here, x2 plus negative 5/4 x4 equals 0, which means x2 is equal to 5/4 x4. And then lastly, x3 minus 3/4 x4 equals 0, which means x3 equals 3/4 x4. And of course, x4 equals itself, just as everything in this universe does. So then, x1, x2, x3, x4 are equal to, cutting to the chase here, x4, I can pull it out of each one, so it's going to be 1/4, 5/4, 3/4, and 1. So what this means is we have a parameter for our free variable here is acting like a parameter, and we can essentially choose it to be anything, and these will go up or down with it. And if we want these to all be integers, we can choose 4. So to clear the fractions, it's free, so we can make it whatever we want. x4 equals 4. So then x1 would be 1, x2 would be 5, x3 would be 3, and as we said, x4 would be 4. So then that means our balanced chemical equation will be, so this was 1 times C3H8 plus 5 times O2 and then that's going to lead, so we have one part propane, 5 parts oxygen, and then that's going to lead us to 3, so we light the match, and then that leads us to 3 parts carbon dioxide, so CO2 plus 4 parts H2O. So for every 1 mole of propane plus 5 moles of oxygen, like of O2, that's going to, after you burn it, lead to 3 moles of carbon dioxide and 4 moles of water, or water vapor. So that may have seemed like a lot of work here, and the way we wrote it, it was. But let's try it again in a shorter, more compact way. So example, and this time what we're going to do is with less writing. just to show you that this is actually, so this one we were working through it to kind of explain it as we did it, but now let's try to do it as quickly and efficiently as we possibly can. So what we can also do is a boron sulfide reaction with water, but let's not worry about that. Let's just write down what the unbalanced equation is and cut to the chase. So B2S3 plus H2O leads to H3BO3 plus H2S. So this is an operation, or this is a chemical reaction. It happens with boron sulfide and water, and you put it in, and stuff happens, and then you get this other stuff. Now let's just think about how we want the vectors to go here. So we can just do it once again in the order that the elements appear in the chemical equation. So we'll go B S H O. So this is kind of an informal way of writing it, but it's fine. So then what we're going to have is for x1, x2, x3, and x4, let's just think about how this is all going to play out. We're going to have here 2 for the boron, 2 for the sulfur, 0 for hydrogen, 0 for oxygen. We're going to have on this one 0 for boron, 0 for sulfur, 2 for hydrogen, 1 for oxygen. Here we're going to have 3 hydrogen, 1 boron, 3 oxygen, but they're all going to be negative. So this is -1 for the boron, no sulfur, -3, -3, and then the last one is going to be minus that equals 0. Yeah, I can write it like this. And then lastly we have 0 for boron, 0 for, 1 for sulfur, but it's on the opposite side, so it's going to be -1. And then 0, -2, and then 0. Sorry, getting a little ahead of myself there. And then 0, 0, 0, 0. Useful for humans to write the augmentation bar, but not necessary. And then we just put it all into the calculator and let things fall out where they may. So by the way, we can just scroll back up to the last time we entered something. Actually, it's easier not to, because when you do that, the calculator starts reformatting in a less easy to use style. So here we go. We've got 2, 0, 1, 0, 0. It's the first row. Semicolon to end the first row. 2, 0, 0, -1, 0, end of second row. 0, 2, -3, -2, 0, end of that row. And then 0, 1, -3, 0, 0. And I'm going to store that once again, as usual, as A. Oh, and a syntax error here. Oh, yeah, sure enough. I put a spurious comma in there. That was meaningless. So, looking at this, does it match? Is it good? If so, then we're off to the races. So, then we go math, matrix, or REF, A, enter, and we get that. Well, it was very tempting for me to actually go back and cut this part of the video out and make a quick little change because in my haste to get through the rest of this section, I made some embarrassing blunders here. They were not of a linear algebra fact nature, but just of a typo nature, just careless typos. But I decided to leave it in because it's a good object lesson, it's good moral. Typos, they happen, but don't panic if they happen. Don't try to be brave about it. Just admit it. And notice right here, there were supposed to be 3 sulfurs in this first molecule. I put 2. Now here's how I knew that something had gone tragically wrong in this. So I immediately hit stop on the video and I thought seriously about cutting this part out, deleting this, and erasing the evidence of my fallibility. But then I decided there's more moral lesson to be had here in showing you how I knew it was wrong, so that way if you do something wrong, you can see that it was wrong. So here's the answer I got according to the calculator. So row reduce 1, 2, 1, 1, 1, which would mean x1 equals 0, x2 equals 0, x3 equals 0, and x4 equals 0, which would mean that the only way that this particular chemical reaction could make sense is if none of this with none of that produced none of that and none of that, which is nonsense. So I knew there was a mistake, then I just had to find where it was, and it was just a typo. And it had to do with the very first column here. That should have been a 3 instead of a 2. So the boron sulfide is B2S3. So then, when I do that, it has now fixed the matrix known as A. It fixed it. I haven't called it A yet. So store it as A. And then go back. So you can actually go to that again. And now that A has changed names, it will now be rectified. 1, 0, 0, negative 1/3. Augment 0, 0, 1, 0, negative 2, 0, 0, 0, 1, negative 2/3, 0, and then 0, 0, 0, 0, 0. We'll typically get a row of zeros in these because we're typically going to end up with one free variable, and to get a free variable from what was a square over here, you need to get a row of zeros. So then, x1, x2, x3, and x4, which means if I juggle things around and cut to the chase, x1 equals 1/3. x4, x2 equals 2. x4, x3 is equal to 2/3. x4 and x4 equals x4. So I set x4 equals 3, so that way everything will come out as integers. So then x1 equals 1, x2 equals 6, x3 equals 2, and x4 equals 3, and then that gives us the balanced chemical reaction here, the chemical equation 1, B2S3, plus 6, H2O. So those react to make 2 moles of H3BO3 plus 3. moles of H2S. So this is the most collapsed it could be as far as trying to write out the fewest steps. And notice there is a risk when you do this of making a mistake. And so watch your step. The more steps you leave out, the more places there might be lurking errors that aren't immediately visible. So watch out. However, the benefits of that are it fit into one little fraction of a page as opposed to the page and a half that the previous version of this did for a simpler chemical reaction. But there it is, nice and short. So this I give you permission to do for problems on problem sets and such, in order to cut out some of the heavy lifting. All right. As for other examples, aside from just these chemical equations, so those will be left actually to your first project. So your first project is going to be coming up at the end of this week. I'll be handing it out, and it will involve what is called network flow, which also is somewhat related to some economics models that they can also be formulated to connect the different sectors of an economy. But anyway, this is going to do it for section 1.6. So after a lot of typos, a lot of mistakes, we finally made it through. And so let's just close the book on this one, and I'll see you for the next episode of Math 261. Till then, bye.